Right, good afternoon, everybody. You guys enjoying the conference?
Yeah.
Yeah? Awesome. So my name is Tabitha. My colleague Kaoru with Tally Technologies, and we are a consumer fintech company based here in San Francisco, and we build consumer apps to help people with financial automation. So I'm really excited to be here today and share with you a little bit about our story and our journey and how our systems have evolved over time, and how we've really been able to add some innovation and fun into building financial systems in general. How many of you have worked in financial services or a fintech company before? Cool, awesome. Has anyone here worked at a earlier stage startup? Maybe Series C or below, et cetera. Awesome. Great, so it's gonna be great. It's exciting, as all of you know, in that space. And so I am very lucky to have been at Tally for about 2 years, and in that time I've seen our systems and our technologies and how we build things evolve. And so what this presentation will go over is to share you a little bit about our journey and how we've transitioned from where we used to be to a new framework called TypeBus, which is how we build reactive microservices over Kafka using Akka Streams and Akka Cluster. So it's gonna be great. So today we're gonna talk about 4 things. First, I just want to tell you a little bit more about Tally and our story, the problems that we're trying to solve as a company, so you have a good understanding of what we're trying to do and then why we're building the products that we're building. The second thing I want to go into is that journey to TypeBus. Like, what were those triggers? What were those things that led us to evolve our technologies, that led us to want to, all the engineering challenges we went through to be able to want us to evolve to a different system, if you will. Kaoru over here is going to talk about TypeBus and the implementation in detail. So he works on the team that maintains the framework and productionizes that framework. So you'll be able to go deep into detail there. And then we'll close off and let you know about some of the things we're working on going forward. Good? Yes, okay. All right, so when I was doing my search for where I wanted to go next, I knew I wanted to go in fintech. I love finance and the blend of finance and technology and helping people with their personal finance. And what stuck out to me about Tally and why I came over here was our mission. Our mission is to make people feel less stressed and better off financially. And there's not a lot of companies that I interviewed at and looked at where that less stressed piece, that emotional piece of helping people with their finances is really a big part of what they do. And it's something that we believe in. And so at Tally, we truly believe in complete financial automation for the average American. We want to build a system, an intelligent service in the background, an ambient service that knows who you are, what you do, what your financial goals are, and it does a lot of the thinking for you when it comes to your finances, and it also does the work for you automatically. Because what we found is the stress of financial management, especially paying off debt, is crippling for a lot of Americans, and that's something that we've been wanting to solve. And so people can spend their time focusing on spending time with their families, spending time with their kids, or just their careers. So when you look at just where we want to prioritize helping people, there's $1 trillion worth of credit card debt in the United States. It's actually been growing quite a bit. And 44% of households have credit card debts that are $15,000 or more. And as you know, credit card interest rates are very expensive, right? So it's a crippling level of stress and anxiety that we found. In fact, if you look at people with good credit scores, they don't even have bad credit scores, just good credit scores alone. 2/3 of them actually have medical levels of anxiety when it comes to managing their debt and trying to overcome it. And when I say medical, it means they're seeking professional help. And so this speaks to us. Like we knew we wanted to at least start with this financial job and help people with that. And so the first product that we launched is what we call Tally Cards. We launched this about 2.5 years ago. It took a while to build, but we finally launched it 2.5 years ago. And what it does is it helps people manage their credit card debt. So our users sign up, they upload their multiple credit cards to our systems, we check their credit score, and we offer them an automated line of credit. And then we use that and optimally pay off their credit cards for them, and they only have to pay us one time. The line of credit that we offer them is lower interest rate than what their credit cards are paying. And so we've been able to help a lot of our users pay off their credit card debt faster, sometimes 10 to 12 years faster, and save $1,000 in interest just by doing this simple job for them. And so the app is doing really well. We've helped a lot of people, but if you remember our mission, which is to help people become less stressed and better off financially, this is only one subset of people in the US that need some help, right? We underwrite our own loans, so we can only, because of the amount of risk we can take right now, we cannot offer loans to people with a FICO score of lower than 660. So of course, that funnel of people we can help is a lot smaller. And so we knew, we need to take financial automation and scale it to the millions, right? And so where we want to help next and what the product we're building next, and which is the impetus of why we're moving to this different framework, by the way, is we want to help people with savings. It is the top of the funnel. If you can't save, if you can't set aside money, you cannot pay off your debt. So over the last year, my team and I have been working on an app called Tally Save. We're in private beta. It hasn't fully been launched yet. It'll be launched next year. But it's the first app that rewards you for saving money, and it's all for free. We found people want to save, they just don't do it for a lot of reasons. And so we want to make saving easy, we want to make saving delightful, rewarding, and we want people to see their progress. And so MVP version of the app it's pretty straightforward. You can save as little as $5 a week. We reward you and we give you points for each time you do something good for your finances. You can take those points and you can redeem credit cards, not credit cards, but gift cards. You can redeem, you can pay off, you can contribute to a charity, and you can help save for different goals, pay off your credit cards, et cetera. So that is the background on what is driving us and moving us to a new technological framework. So on the engineering team here at Tally, so we're a Scala shop, and we're excited. Like, we're getting this new app that we need to build over the last year, and the requirements to build this app was as follows. First of all, product told us we need to build this app and have it have the potential to scale to the millions, which is awesome. It has to have that room. The second thing we need to build is that reward system, right? We offer real-time points, we award points. That has to be really responsive. Our systems have to respond and react and process events in real time. Also, the money transfer process, it has to be reliable. It has to be something that is consistent, reliable, and because it's a key user function that we have. And so we knew that those are things that we need to build for. Our constraints is we want to stay within the Scala ecosystem. We're passionate about Scala and functional programming in general. And we also wanted to avoid some of the engineering challenges that we went through in the early stages of our company as we were trying to build products really fast. So I want to start off and go over what some of those challenges were so you can understand why we moved to TypeBus. So in the past, and our Tally Cards product actually still runs on this system. We built services pretty traditionally. 5-6 years ago, this is how most services were built, right? So client talks to the ELB. Goes into the API layer. We use Akka HTTP, and then down to the service layer. So IDL, thrift, finagle, et cetera, all the way down to repository to the database. And as you can see, there was schema first. There are many communication layers that communications would have to go through. On top of that, multiple layers of serialization and deserialization, a lot of boilerplate, code gen, et cetera. Services talk to each other through RPC. So we had to pull in dependencies from the clients of each service, et cetera. So it wasn't easy to stand up a service. I mean, it worked fine for us, but it was very error prone. There's a lot of areas that people can make mistakes. And I know some of you might have worked in this area before. So it works really well for us. It's just, we knew we needed something different for Tally Save. Another challenge that we had was that we started building what was called a distributed monolith. So even though they were microservices, they were so intertwined that they really weren't, right? So tight coupling, complex web of dependencies. We had shared data stores, our code was shared, our data models were shared and pulled in. The responsiveness, resiliency of those systems was not that great. On top of that, our data pipeline was really brittle. They were pretty much ETLing data from our databases. Nothing was in real time. Like, eventing wasn't really a first-class citizen. We didn't really use eventing. And so that was exactly where we wanted to move to. So when you add all of these problems together, what you have is just really slow, error-prone development cycles. That was frustrating for our engineers. It made onboarding difficult because the systems are complex and hard to reason about. And we knew if we wanted to scale not just for a product, but for our organization, we had to figure out a different way to build things. So Tally Save, when we started building that new system, we wanted to take a risk and try we want to stay within Scala, but try to do things differently and go reactive and build our architecture event-based. So what we did was we made a wish list of things that we needed for Tally Save, right? We knew that we wanted the event-driven architecture to be the center of what we build. We wanted to make sure that if we can build a framework that can help us build these reactive microservices, we wanted to have an API that was easy for our developers to be able to hook onto Kafka, hook onto whatever transport layer we want to use, and be able to spin up services easily. We wanted the ability for code-first data modeling to prevent some of those serialization issues that we saw before. Wanted to avoid traditional service discovery and also we wanted to make asynchronous jobs and managing throughput for those asynchronous jobs, which is the money transfer jobs, pretty easy. So it's a hefty wish list, but we wanted to build a framework that can help us with this. We were looking around, and this was a year and a half ago or so. It was hard for us to find something that truly fit all these needs. We had an engineer, a really smart guy out in Vancouver, and he was working on a side project that he called TypeBus. It was a very light version of this. It didn't cover all the features, but it was something he brought to us, and he suggested we try looking at this as a framework and toolkit to build microservices. And we're like, why not? Why not try it? And so we took a look at it, and we really liked it. We thought there's a lot of potential. So we worked together and productionized and maintained that code base, and we now use TypeBus to build microservices for TallySave. And so what TypeBus is, and maybe after Tally touches it, you can call it TallyBus. But it is a mildly opinionated framework for building reactive microservices in Scala. It supports and abstracts away a request and response pattern over a transport protocol. So we use Kafka right now, but it could really lay over anything. It has an easy-to-use API, so it's easy for developers to interact and just either consume data off Kafka, et cetera, and also spin up services and service contracts. And so it solved a lot of problems for us. We worked a lot, and just to give you a sense of, at a high level, how our services work on this platform. Each of our services is built in this TypeBus framework, and they all communicate and interact with each other through Kafka. So the event bus is really the source of truth. So that, at a high level, is how our evolution of technologies has come about, and now I'll pass it on to Kaoru, and he will go over in more detail about how TypeBus works under the hood.
Great. Thank you, Tabitha. All right, so let's talk about TypeBus implementation. So just a disclaimer here, I'm going to go over some concepts from Kafka, Akka Streams, and Akka clusters. I'm not going to get a chance to really dive deep into the details of these, but I am going to be able to show you how we're combining these technologies to hit our design goals for TypeBus. So let's bring back those design goals. The first thing we want to do is have convenient service updates. So what does this mean? As a service, I want to be able to publish my state to the world and have anybody listen to that update. By the very virtue of using TypeBus, we can accomplish this. Kafka. So I can publish my state to Kafka, and other services can know that I made a state change. Cool. We're done, right? Let's just go home. No, I'm kidding. All right, so let's bring back those design goals. We met the first one. The second one we want to do is have an easy and convenient API. So what does this really mean? Is that our engineers should be able to publish, consume, and also do request and response patterns with a single API. All right, so what does that look like? Let's bring up some code. Here we have a cat client, and this cat client allows you to get a cat given a name. So we have a method definition here on line 2 that says, give me a cat by the name. It's going to return a future. Once that future resolves, you'll get back a cat, and then you go on your merry way. On line 6, what we're doing is we're telling the Kafka consumer to look out for a cat message. I'll get into a little bit more detail on how we're accomplishing that. On the server-side code, we have a cat ranch. And so this cat ranch is looking out for fetch cat messages. And the fetch cat, once it has a fetch cat message, it'll pass it to an internal actor and then send back a cat to TypeBus. And the reason why we're returning a future is so that TypeBus knows that the message handler has successfully handled the message. Once it knows that, then it can confirm it back with Kafka. On line 8, we have a listen to adopt cat message. And this is basically the subscribe pattern. So if I want to know that you adopted a cat, that you adopted a cat, or that you adopted a cat, I can listen to those events, do something with that, and then confirm it back to Kafka to make sure that I have successfully processed that message. Line 12 and 13 is what we're doing is we're registering these methods into TypeBus so that when TypeBus sees these messages coming off of Kafka, it knows where to forward these messages to. Great, so how do we use this client? Well, first we have to initialize it, and then we say, give me a cat named Butters. I get back a future, and I map over it. I get a Butters cat and say, I really like Butters. He's really fluffy and, cuddly. So I'm going to go ahead and say, I'm going to adopt this cat. I'm going to announce it to the world by putting this message back onto Kafka. All right, so let's really think about how we can accomplish this request and response pattern over Kafka. So here I am announcing to the world, I want cats. I put it onto Kafka, the cat ranch sees this request, and we forward that, the cat ranch will respond with a cat, put it back onto Kafka, and I'll get a cat back. Now, if you ever use Kafka, you're probably thinking to yourself, whoa, 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 whoa. That's not how Kafka works. And what is this bear doing on the screen? And you're right. Kafka doesn't work that way. In reality, it looks more like this. We have a me cluster that was represented by 3 different VMs. And that request could start from me1. So me1 says, I'm going to request a cat. I put it onto Kafka. The cat ranch sees that request, sends back a cat through Kafka, and then forwards it to maybe me3, because Kafka is managing the message distribution. Me3 gets a cat on its lap. Doesn't know what to do with itself. Do I pet it? Do I feed it? What do I do with this cat? So in reality, this is something that we're going to be doing, or something that we're doing to finish the response cycle is that we're starting up a Akka cluster actor on me1. So me1 is actually an Akka cluster. So when we start up this actor, it has an address. And we insert that address into the request. And that request goes to the cat ranch. And the cat ranch forwards back the original requester's address so that when me3 gets that message and that response, it knows, oh, wait a second, this cat isn't for me. This cat is actually for me1. So I'm going to go ahead and forward that cat to me1. And that's how we accomplish the request and response pattern. And this is somewhat similar to how Akka implements their ask pattern. All right, great. So let's talk about code-first data modeling. With Thrift, Avro, Protobuf, you first have to define a schema. And then from that schema, you're going to get a plain O Scala object. Well, that means that our engineers need to learn the semantics of this IDL. And then we didn't want to jump that hurdle because we wanted to move quickly. So instead, we want to work with just Scala objects. So let's go back to the cat client definition. Fetch cat and cat are actually just case classes. So how are we sending these things over Kafka? We're using a library called Avro4S. And basically what this does is it'll take a case class, serialize it down to Avro bytes. TypeBus will then wrap that in an envelope with metadata and attach the canonical name of that case class. Then serialize it again with Avro4S because it chortles all the way down. And then we will put it into Kafka. When we pull those bytes off of Kafka, we'll do the reverse. We'll deserialize it back into the envelope, and then we'll deserialize it back into the case class so that our code, our business code, only deals with Scala objects and doesn't have to deal with this deserialization, serialization dance. You also notice that the topic name is the same as the canonical class name of the message that gets inserted to it. And we're using the same Java convention, naming convention, to map it to a topic. And this really allows us to manage our topics better so that we're not wondering what message is in this topic. We already know by the name of it. Great. So now let's talk about service discovery. So service discovery, basically, you might think, okay, well, I need a new service. So that means I probably need to spin up a load balancer. I probably need to spin up some servers. And I probably need to create a DNS name that other services can talk to. And then I need to reconfigure the clients to say, like, hey, this is a new service that popped up. Here's how you talk to it. Here's the DNS name. Here's the port, et cetera, et cetera. And that's a lot of hurdles when you're trying to move fast. So what we're doing is we're relying on Kafka's message management to remove that hurdle. So what does this look like in practice? Say we are in production and I'm requesting cats and I'm getting cats. I'm happy, life is good, right? The cat ranch is providing me with those cats, but then product kind of comes to us and says, well, these cats are pretty miserable. They're cooped up in cages. Maybe they're too close to each other. They're not really happy cats. So let's come up with a free-range cat ranch. And this free-range cat ranch is going to have fields. It's going to have trees. It's going to have all the catnip that the cats can take. And they're just going to do cat things, right? They're just going to be happy cats. So we work hard. We spin up this free-range cat service. And Kafka manages the partition. So it now starts sending some of those requests to the free-range cat ranch service. So what this means is that now the team can tear down the old cat ranch, and all of a sudden, I'm still getting cats. I'm still requesting cats. I'm still getting cats back. And I'm none the wiser of where the cats are coming from, whether it's the cat ranch or the free-range cat ranch. And this flexibility allows us to spin up and tear down services relatively quickly. The last thing we want to tackle is configurable throughput management. So in the financial space, especially when we're talking about credit card debt, at the end of the month, at some given time, we want to start paying off our customers' credit card debt. So we kick off all these jobs. And when you think about these jobs, they create a lot of database queries. What we don't want to do is we don't want to DDoS our databases and prevent our mobile clients from accessing the data because that might seem that we're down. So we want to really control the throughput that's coming into our databases. And the way that we're doing that is by using Akka Streams. So you can imagine one of these jobs kicking off, putting 150 operations per second. Our database on the far right can only handle about 10 requests per second. This is a contrived example, but it's a sad little database and can only handle 10 requests per second. So we're using Akka Streams to really control that rate and that throughput so that our databases has enough resources to also serve out our mobile clients' requests. So that we don't seem like we're down or slow when these jobs are running, and we can still satisfy the needs of our jobs, but we can also still satisfy the needs of our mobile clients. Akka Streams is really great for also describing these complex graph or it has a expressive graph DSL that allows us to add some retry logic into the graph. So what does this mean? If for whatever reason a message is dropped because of network, magic, voodoo, whatever, we want to be able to retry that message because that message represents someone's credit card debt. We don't want to miss a payment. So we take that message, we add it back to a retry source, and Akka Streams allows us to express a flow which will take some messages from the Kafka source and some messages from the retry source and still maintain that 10 operations per second throughput to the message handler. The message handler is oblivious of whether this message has been retried previously or is a brand new message. All it really cares about is handling that message and making sure that operation succeeds. Great. So let's go back and talk about all the things that we talked about. So the first thing we want to do is have convenient service updates, and we do that by Kafka. Kafka is managing our messages and making sure that any new service can start subscribing to updates. We have an easy and convenient API that can publish and subscribe and also send out requests and get back responses. We have a code-first data modeling with Avro4S, and Kafka is managing our service discovery because we don't want to jump the hurdles of setting up a new network infrastructure whenever we spin up a new service. We also have configurable throughput management with Akka Streams to really allow us to control the throughput of these asynchronous jobs. All right, so what's next? We want to start thinking about distributed tracing with TypeBus. You can imagine a message being consumed by 6 different consumers, and all of a sudden you're looking at a trace with one message with 6 subgraphs. And those graphs can be graphs of graphs of graphs of graphs, and it turtles all the way down. So we want to come up with a way to manage that distributed tracing in an eventing system. We also want to start thinking about how we could use and leverage production data to load test our staging environments. You can think about maybe we want to replace our sad little database that's doing 10 operations per second for something that's more scalable. And instead of creating the data ourselves because, we don't predict the future and we can't predict how clients are actually using our applications. We want to use real production data so that we're not missing out on any edge cases. And we want to make sure that our systems that we deploy to production are predictable in a way that makes sense to our business. All right. So that's the future of TypeBus. If you have any questions, these are the ways of means of contacting us. I want to thank you all for listening to us. Thank you. Oh, we have time for questions. Great. 5 minutes for questions. Oh.
Hey, that was a great talk. Thank you. I had 2 questions. One was, for your IDL definitions, you mentioned that you use Scala objects, and then you serialize it using whatever that framework was called. But how do you share objects across different services?
That's a good question. So right now we're in the transition of, we have a monorepo, and right now we are using SBT to build and compile that code. We've slowly discovered that that isn't going to be scalable, and so right now we're in the middle transitioning to Bazel. But the way that we share that code across our microservices is by using a monorepo. Gotcha.
And I'm curious, are there any other frameworks in the industry that are comparable to what you just talked about?
To be honest, I'm more familiar with Kafka than I am with Scala and Okta. And from my experience, there isn't something out there like this that can fulfill a request and response pattern with Kafka. They're so similar.
In the same idea, how do you do a refactoring? Let's say, for example, your fetch cat message. How would you rename something, or in this case it's a really simple example, but how would you add a field or remove a field since it's gone into Kafka and the topic name matches the class name?
Right. To make sure I understand the question correctly, it's how do you handle the migration of the message itself, right? Great. So Avril 4S, or excuse me, Avril is a version schema. It has versions of schemas. So as you add a field, you can say that this is the schema that produced that field, and it knows how to read it and create it back a Scala case class. And vice versa, if there's a new field, you have to make it optional to say, if I'm reading it with an old schema, just ignore that field. And it works somewhat similar to protobuf, but protobuf actually uses numbers where Avril uses ordering. But generally, we're relying on Avril to handle the schema migrations. Oh, yeah, go ahead.
Yeah, I'm not overly familiar with Kafka, but if I recall correctly, if you're subscribing to a topic, there are no particular restrictions on who can read the messages. Mm-hmm. And so I'm curious, do you have any data that you're transferring over this bus that you only want certain services at your company to read? And how do you prevent other services from not accessing that data, or from accessing that data?
Gotcha. So the question again is, we have a topic, and I want to make sure that only certain services are listening to that topic. So there are multiple ways. The easiest answer is just making sure that your code reviews are on point. But the better answer is Kafka itself has role-based security, so you can limit the amount of services that are actually talking to those topics by assigning those permissions to those services.
Hi there. I was curious how you were doing the load testing and staging with production data, and how you ensured no PII is being leaked and things like that.
Great question. So this is a thing that's in my mind right now, and not something that's in production. It's a future project. If you were to ask me off the cuff, just off the top of my head, how I imagine we would do this, is that we would create a streaming app, a streaming Kafka app that would potentially scrape out any PII data. But also, to be clear, we don't put PII data in Kafka in the first place. So once we have this streaming application, we can then send it to a different cluster, and from that cluster we can do whatever we want with it. Does that answer your question? Cool, thank you. There's one more right here.
Yeah, I was wondering if you can share some data on latency.
Yeah, that's a great question. So again, like the app right now is in private beta, but the latency that we are looking at, depending on the the use case, is around 50 to 150 milliseconds, and it depends on really on the workload and what the message handler is doing. We honestly haven't spent a lot of time on tuning the Kafka producers or the Kafka consumers, so I think there's a lot of wiggle room in those perspectives. But we're really not, we're relying on our data infrastructure, or sorry, our infrastructure team, or what we call dev productivity tools, dev productivity team, to really fine tune and make sure that the latencies are acceptable to product. So right now it's too early for me to say that it's going to stay in those bounds, especially because the amount of data that we see is not really where we want to be. So maybe we'll give another talk on the performance issues that we might see in the future.
Do you guys have any view to know where your request is in this Kafka topics? Like how would you know?
Sorry, can you speak more into my?
How would you know where is your request is in all these topics that you have? Like let's say a customer request comes in. Like how do you debug it? How do you troubleshoot where the request is? Is it dropped down in the middle, or is it where it is?
Yeah, so let me make sure I got the question correct. You're thinking about how do I trace back where this request came from? Is that correct? So right now, what we're doing is every time a producer produces a message, we're creating a UUID with that message. So we can trace back where that UUID came from and what service it came from. Right now, our app is relatively small, so we don't have a problem of like thousands of microservices talking to each other. I think in the future, it could be more sensible to add like a service name to that UUID so that's more easily trackable. But also, we want to start investing in distributed tracing, which will hopefully answer some of those questions of where this request came from. Does that answer your question? Oh. Gotcha. So you're talking about like if the message handler is latent, do you want to know where in the Kafka topic? Yeah. So I don't actually have a good way. I don't think there's a good way of keeping track of an individual message, but we are collecting metrics on the end when we consume the message off of Kafka to say when was the message created, and when is the time that I saw it. Create that diff and then put it on a graph. So we have alerts on making sure that our consumers are not far behind. Do we have time for more? Because I think he might have another one. No, okay, sorry. You know what, we're going to be right outside these doors. Let's talk more. Thank y'all.